Welcome back to the deep dive. Today we are clearing the desk. We are sweeping away, you know, all the hype cycles, the JavaScript frameworks of the week, and those theoretical computer science papers that look great on a whiteboard but are a total nightmare in production. We are getting down to the metal. We are talking about the language that, well, effectively runs the modern cloud. We are talking about Go, or as many call it, Golang.
It really is the language of infrastructure. I mean, if you peel back the layers of Docker, Kubernetes, Terraform, CockroachDB, Prometheus, all that bedrock of the modern internet, it is almost entirely written in Go.
It's like the concrete.
It's the concrete of the digital world, absolutely.
And looking at our research stack for today, the theme that just keeps jumping out isn't innovation or sparkle. It's this phrase that appeared over and over again, ruthless pragmatism. That seems to be the entire ethos here.
That is the perfect way to describe it. I mean, Go is an incredibly opinionated piece of engineering. It doesn't care if you think it's pretty. It just cares if it works at scale.
Yeah. So here is our mission for this deep dive. We are explicitly not doing a Hello World tutorial. That's not the goal. We're assuming you, the listener, might know what a variable is. Maybe you're coming from Python, Java, or Node, and you want to know the engineering reality of Go.
Right. What it's actually like on the job.
Exactly. We want to go from the philosophy that drives it to the syntax traps that drive people crazy, all the way to what the source material calls the dark arts of production performance.
And to really understand that reality, you have to start with the origin story. It explains everything about why the language feels the way it does.
Okay.
Go wasn't a research project at university. It wasn't designed to prove some, grand thesis about type theory. It was designed at Google back in 2007 by absolute legends.
We're talking about Ken Thompson, Rob Pike, and Robert Gressmer. I mean, Ken Thompson designed B, which directly led to C, and he was one of the core creators of Unix.
I mean, yeah.
These aren't fresh grads. These are people who have seen 40 years of software mistakes.
Exactly. They were looking at the very specific, very painful problems Google was facing at that scale. They had these massive code bases, millions and millions of lines of C++, thousands of engineers all working in the same repo.
And the build times were legendary.
Oh, just insane. We're talking 45 minutes just to compile a single binary. So they were dealing with that, and also massive distributed systems running on huge networks of machines. They didn't need a language that allowed for clever, complex abstractions. They needed something else entirely.
They needed something stable, readable,
and fast to compile. That was a huge driver.
There's this great point in the notes about simplicity is king. Go has only 25 keywords.
That's miney.
It is incredibly small. I mean, compare that to C++ or C#, which have vastly more. The core philosophy is that if a feature makes the code harder to read, even if it makes it a little easier to write, Go rejects it.
So readability over writability.
Every single time. The goal is that you should be able to jump into any Go code base anywhere in the world and understand what it's doing in about 5 minutes. Which is a huge mindset shift, right? If you're coming from Ruby or modern JavaScript, where you can write some clever one-liner that does 6 different things and looks like magic, Go is going to feel, well, plain.
It will feel restrictive. It's going to feel boring. And that is the first warning we have to give. If you try to write Java or Python in Go, you will hate it.
You'll be miserable.
You will fight the language every single day. You have to accept the Go mindset. There is no extends keyword. There's no inheritance in that traditional sense. You don't get a massive standard library of generic collection types like you might in Java.
Yeah.
You have to build what you need, often from first principles.
So let's unpack that ruthless pragmatism a bit more. It feels like Go is almost protecting engineers from themselves. Is that fair to say?
In a way, yes. It intentionally limits the number of ways you can solve a problem. The benefit of that is when you read someone else's code, it looks and feels a lot like your code. It removes that cleverness that so often leads to unmaintainable technical debt down the line.
Okay, let's get into the mechanics. Because even the way a Go project is laid out on your hard drive is, well, it's not just a suggestion, is it? It's practically a mandate.
It really is. In so many other languages, you can put your files wherever you want. It's the Wild West. In Go, there is a community standard layout that pretty much everyone follows. If you don't follow it, you are just fighting the tooling and the entire ecosystem.
The first thing you're going to see at the root is go.mod.
Yeah, that's the heart of modern dependency management. It defines your module name, the Go version you're targeting. We don't use the old GeoPath anymore, and thank goodness for that, we use Go modules.
And this is how you get reproducible builds.
Exactly. It locks your dependencies to specific versions so that it works on my machine, Actually means it's going to work on the server too.
But then you get into the folders, CMD, internal, PKG. Let's break these down because internal specifically blew my mind a little bit. It's not just a naming convention, right?
No, not at all. And this is, I think, unique to Go. Internal is a feature where the Go compiler itself enforces privacy. If you put a package inside a folder named internal, the compiler will literally refuse to let any external project import it. It is strictly for your own project's use.
That is wild. Usually private in software just means please don't touch this, or maybe you slap a protected keyword in a class definition. But here, the directory structure itself dictates visibility to the rest of the world.
Exactly. It's a fantastic feature because it prevents other developers from depending on your unstable implementation details. If you want code to be reusable by the world, a public library, you put it in PKG.
Okay.
If it's just for you, your own application's business logic, it goes into internal. And CMD is where your main applications live, but the rule there is to keep it absolutely minimal. Just wire up your dependencies and start the application. Don't put business logic in CMD.
Right. Now, we touched on this, but let's drill down. You mentioned there's no inheritance, but I see Go code that look a lot like inheritance. You have structs inside of other structs.
That is embedding. And it is the single most common trap for object-oriented programmers coming to Go. You can embed one struct, say base, inside another struct, say user, and user will automatically have the methods of base.
So I can call user.base method. That sounds exactly like inheritance to me.
It behaves like it syntactically, I'll give you that, but it's purely composition. And here's the crucial distinction. The user struct is not a base struct.
Yeah.
You cannot pass a user to a function that expects a base.
Oh, so there's no polymorphism.
None. In Java, with a class hierarchy, you could absolutely do that. In Go, the compiler will yell at you. It forces you to build complex types by gluing smaller pieces together, not by creating a family tree.
Right.
It forces you to think about has relationships. A user has a base instead of is relationships.
That's a subtle but, wow, a massive difference. It prevents those deep, brittle inheritance trees where changing a method in the grandparent class breaks the entire application 3 levels down.
Precisely. It keeps the dependency graph flat.
Okay, let's talk about the gotchas, the syntax traps. Because for such a simple language, there are some serious bear traps waiting in the woods. The first one in our notes is shadowing.
Oh, the shadowing trap. This happens because of the short declaration operator, the colon equals, the colon equals.
Yeah.
It's so convenient everyone uses it. You use it to declare and initialize a new variable.
Right.
But if you use it inside a block, like an if statement, you might think you're updating a variable from outside the block, but you're not.
Walk us through an example of that.
Okay, so imagine at the top of your function you have error nil. You've declared an error variable. Then inside an if block, you write count error, some function. Because you use it. Again, you have just created a new variable named error that only exists inside that if block. It shadows the outer one.
Oh, wow.
You check it, it's nil, you move on. But as soon as that curly brace closes, that new error variable vanishes. The original error outside the block is still nil. You've potentially swallowed a real error.
That is insidious. That's a really tough bug to spot in a code review.
It is a classic source of bugs where you think you've updated a state or handled an error, but you've actually just updated a shadow variable that disappears. The fix is to be so careful with them versus just a plain.
Okay, moving on to data structures. Slices versus arrays. This is fundamental to Go, but it works very differently than, say, C or Java arrays.
It does. First thing to know is, in Go, an array has a fixed size. 5int is an array of exactly 5 integers. You almost never use these directly in your function signatures.
You're always using slices.
Always. A slice is a dynamic view that is backed by an array. Think of it like a little struct that has a pointer to the start of data, a length, and a capacity. It's a window frame looking at a section of a long strip of memory.
But here is the append gotcha. A slice has a len, length, and a cap opacity, and those are not the same thing.
They are not. And this is key. If you append data to a slice, and it fits within the capacity of that underlying array, it's super fast. Go just updates the value and increments the length. But if you exceed the capacity,
Then Go has to find a new place for everything.
a whole new place. Go allocates a completely new, larger array, usually doubles the size. It copies everything over from the old one, and then it points your slice to this new chunk of memory.
Which happens transparently, which is great for usability, but
But if you aren't aware of it, you can cause serious performance hiccups. If you're appending in a tight loop, you might be triggering these massive allocations and garbage collection cycles over and over without even realizing it.
and there's an even darker side to slices too, the memory leak trap. This one scared me when I read about it in the
This
notes.
is a very, very common production issue. So imagine you load a massive, say, 50 megabyte log file into memory, a huge array of bytes. Then you want to keep just a tiny 10-byte snippet of that file. So you take a slice, file 0.00.
Seems efficient. I'm only holding on to 10 bytes.
You think you are holding 10 bytes.
Right.
But because that slice header contains a pointer back to the start of the original 50 megabyte array, the garbage collector cannot clean it up.
It can't free the memory.
It can't. As long as that tiny 10-byte slice exists, the entire massive array stays in RAM.
So you're holding a thread, but the thread is attached to a piano.
That is a perfect analogy. You are dragging the piano around your memory for no reason. The fix, which we'll get to, is to explicitly copy those 10 bytes to a brand new slice so the big array can be released.
Wow. Okay, we'll talk more about memory fixes in the dark arts section, but that is a good tease. What about maps?
Maps for the Wild West. First rule, iteration is random. If you loop over a map, do not ever, ever expect the keys to come out in the same order twice.
Is that just a side effect of the implementation?
No, it's intentional. Go actually randomizes the starting offset of the iteration on purpose to stop you from writing code that relies on a specific order.
That's amazing. They break it on purpose so you don't write bad code.
Ruthless pragmatism.
Yeah.
But the real danger with maps is concurrency. A standard Go map is not safe for concurrent read and write.
What does that mean in practice?
It means if one Go routine is reading from a map and another one writes to it at the very same time, the program doesn't just return an error or give you weird data, it crashes. Hard, fatal error.
So you have to lock it.
You must use a mutex or the specialized sync.map type. And one more map quirk, the zero value. If you read from a map and the key doesn't exist, Go doesn't throw an exception or return nil. It returns the zero value for that type, like 0 for an int or an empty string for a string.
Which can be really confusing if you don't check if the key actually existed. You might think, oh, the user's score is 0, but actually the user doesn't even exist in your map.
Exactly. You have to use the two-value assignment, okay, my map key. That second Boolean, okay, will be true if the key was there, and false if you just got a ghost 0 value.
Let's move on to control flow. This part of the language seems, well, minimalist.
There's only 4. No while, no do while, just 4. You can make it behave like a while loop with for condition, but the keyword is always 4.
And the defer statement. I love defer. It just feels so clean.
It is incredibly elegant. Defer schedules a function to run immediately before the surrounding function returns, for any reason, a normal return, a panic, whatever.
So it's perfect for cleanup. You open a file, and on the very next line, you write defer file. Close.
And you never have to worry about it again. You don't need a finally block. You know the file will get closed.
But there's a catch with the arguments, right?
Yes, and this trips people up. The arguments to the deferred function are evaluated when the defer statement is reached, not when the function is finally executed.
Ah, okay.
So if you defer a log statement like defer fmt.println, finished with value, myvar, the value of myvar that gets printed is the value it had when the defer line was hit, not the value it has at the end of the function.
Got it. And defer is LIFO, last in, first out.
Like a stack of plates. The last function you defer is the first one that will execute on exit.
Now, we absolutely have to talk about the elephant in the room. The thing that people complain about the most when they start writing Go, error handling.
If error, nil.
It's everywhere. The notes say it can be 30% of your code base.
It's verbose. There is no try-catch. There are no exceptions. Errors are just values. They are returned by functions like any other result.
Why make us type this over and over and over? It feels archaic.
Because it forces you to acknowledge the error path. In languages with exceptions, it's very easy to wrap a huge block of code in a try block and just stick a generic catch at the end and hope for the best. Or even worse, let an exception bubble up invisibly, 3 or 4 layers, and you have no idea where it came from.
So it's about visibility. You see exactly where things can fail on every single line.
Exactly. The control flow is explicit. You cannot ignore an error unless you consciously choose to by assigning it to the blank identifier, the underscore, and that's a deliberate action.
So panic exists, but it's not for errors.
Right. Panic is for truly unrecoverable states like, I cannot load my configuration file and the application literally cannot start. It's for programmer bugs, not runtime errors.
And recover is how you can catch a panic, but you shouldn't be using it to emulate try-catch.
You really shouldn't. The standard library's HTTP server uses recover so that if one request handler panics, it doesn't bring down the entire web server. That's a legitimate use case. But in your application logic, handle errors as values.
Let's shift gears now to memory mechanics. This is where we start peeling back the layers a bit. You mentioned stack versus heap earlier. Why does a Go engineer need to care about this? I mean, Go has a garbage collector. Shouldn't it just handle it for us?
It does handle it, but if you want performance, which is usually why you're choosing Go in the first place, you need to understand escape analysis.
Escape analysis sounds like a Prison Break movie.
That's sort of like that.
Yeah.
Ideally, for performance, you want variables to live on the stack. The stack is incredible fast, it's managed per Go routine, and allocation and deallocation are basically free. It's just moving a pointer up and down.
And the heap is slower?
Much slower. It requires the garbage collector to come along and scan it and clean it up, which costs CPU cycles. So the less you use the heap, the faster your program generally runs.
So how do you keep things on the stack?
Well, the compiler decides for you. That's escape analysis. The compiler analyzes your code and asks, can this variable's lifetime be proven at compile time? If a variable is created in a function and never used outside of it, it stays on the stack.
But what if I return a pointer to it?
That's the key. If you create a variable inside a function and then return a pointer to that variable, the compiler says, uh-oh, this variable is needed outside of this function's scope. So it escapes to the heap.
Because if it stayed on the stack frame would be destroyed when the function ends, and the pointer would be pointing to garbage memory.
Exactly. Understanding this helps you write hot paths code that runs thousands of times a second without creating a ton of garbage that slows down the entire system.
This connects directly to the idea of receivers, right? When you define a method on a struct, you can use a pointer receiver or a value receiver.
Yes, and this is a common point of confusion for beginners. The rule of thumb is actually pretty simple, though. If you use a pointer receiver that's func, as struct, you are passing a reference to the original struct.
So if you change a field inside that method, it changes the original.
Correct. You're mutating the state. You also use a pointer receiver, if the struct is very large, to avoid the cost of copying the entire thing every time you call the method.
And if you use a value receiver, func, s, struct,
then you are passing a copy. The struct is effectively immutable within that method. If you change a field, you are only changing the copy, not the original.
So for a massive struct with a ton of data, I probably always want a pointer receiver just to avoid copying all that data around.
Generally, yes, for performance. But for small, simple structs, like a point with just an x and a y coordinate, value receivers are perfectly fine and are often safer because they guarantee the original data isn't changed by accident. The most important thing is consistency. Don't mix pointer and value receivers for the same struct. It gets very confusing.
Okay, we've covered the core mechanics. Now let's talk about the superpower of Go, the thing it's famous for, concurrency.
CSP, communicating sequential processes.
And the mantra that everyone quotes is, do not communicate by sharing memory, share memory by communicating.
It's a beautiful concept, and it's fundamentally different from the threading model in most other languages. In Java or C++, say, you have threads sharing a variable, and you have to put locks, mutexes around that variable so they don't corrupt it while fighting over it.
A lot of complexity there.
A lot. Go flips it on its head. Instead of locking a shared variable, you pass the data from one thread of execution to another. You hand it off cleanly.
And the workers here are not threads, they're Go routines.
Right, and Go routines are incredibly lightweight. A typical OS thread might take 1 or 2 megabytes of stack space just to be created. A Go routine starts with 2 kilobytes.
That's 1,000 times smaller, so you can spawn hundreds of thousands of them.
You absolutely can.
Yeah.
And Go uses an MN scheduler. It multiplexes mGo routines onto N operating system threads. It's extremely efficient. But, as always, there is a trap.
There's always a trap.
Just because you can spawn 100,000 Go routines doesn't mean you should. If they're all fighting for the same CPU core, or they're all waiting on the same database lock, your program will still crawl to a halt. Concurrency is not parallelism.
So how do these Go routines talk to each other? You said they pass data, they use channels.
The pipes. Channels are typed conduits. You can have a channel of integers, a channel of structs. You push a value in one end, and another Go routine can pull it out the other end.
And there are two main flavors, unbuffered and buffered.
Unbuffered is synchronous. This is a critical concept to grasp. If I send a value into an unbuffered channel, my Go routine blocks. It stops running until your Go routine, the receiver, is ready to take the value out.
It's like a handoff in a relay race. I can't let go of the baton until you actually grab it.
That's a perfect analogy. It forces a synchronization between the two. A buffered channel, on the other hand, has a queue. It's like a bucket. I can drop the baton in the bucket and keep running as long as the bucket isn't full.
But channels have a minefield, according to the notes, the closed channel.
This is where things get dangerous. If you send data to a channel that has already been closed, panic. Your program crashes.
Okay.
If you try to close a channel that's already closed, panic. Your program crashes.
So closing a channel is a risky operation.
It is. The firm rule is only the sender should ever close a channel, never the receiver. And there's a neat trick. If you read from a closed channel, you don't block. You immediately get the zero value for that channel's type, over and over.
Which is actually useful sometimes.
It's very useful. It's how you can broadcast a stop signal to many coroutines at once. You close one channel, and they all wake up.
Then we have the select statement.
The select statement is like a switch statement, but for channel operations. It lets a single coroutine wait on multiple channels at once. It will execute the case for the first channel that becomes ready.
And this is crucial for things like timeouts.
It's the only safe way to do them. You can say, wait for a message from this work channel, or wait for a message from this time after channel. Whichever one happens first wins. It prevents your coroutines from getting stuck forever.
That brings us to a really interesting piece of advice in the notes. Mutexes versus channels. It says, new Go developers want to use channels for everything.
They do. They hear about CSP, and they try to build these incredibly complex channel-based systems for everything. They over-engineer it.
So what's the practical advice?
The advice is this. Use mutexes for protecting the internal state of a struct. Things like a counter, a cache, or a map that's a field on your struct. Mutexes are fast. They're handled at the CPU instruction level.
Can channels?
Use channels for passing ownership of data between coroutines or for orchestrating and controlling the flow of the program.
So lock your data with mutexes, move your data with channels.
Precisely. That's a great way to put it.
Moving on to what the notes call the nervous system of a modern Go application, the context package.
You cannot write production Go code today without understanding context. It is the standard built-in way to handle request scope, data, cancellation, and deadlines.
And you see it everywhere. It's almost always the first argument in every function. CTX context dot context.
It has to be. Imagine a web request comes into your server. It needs to trigger a database query, an API call to a third-party service, and some logging. That whole chain of operations, that whole tree of calls, is tied together by a single context object.
And the killer feature here is cancellation propagation.
This saves companies so much money. If the user closes their browser tab, the HTTP connection drops. The server knows this and cancels the parent context. Because you pass that context down to your database query function, the database driver sees the cancellation signal and can stop the query immediately.
So you don't waste 5 seconds of CPU and database time computing an answer that nobody's waiting for anymore.
Exactly. It's incredibly powerful for building resilient, efficient systems.
But the notes have a big warning sign next to values in the context. Context what with value.
Yeah, you should use this very sparingly. It allows you to store arbitrary key value data in the context. It's acceptable for things like a request ID or a user ID for tracing and logging.
But not for your database connection.
Please, never for your database connection. Do not use it for dependency injection. It destroys type safety because the value method just returns any. You lose all the benefits of Go's compiler. You have no idea what's actually in there.
Okay, let's talk testing, the Go way.
It's built right in. Go test. You don't need to pull in a big third-party framework like Gnit or Jest. And the dominant idiom, the way everyone writes tests, is table-driven tests.
I've seen these. They're really cool. You define a struct that holds your test case inputs and the expected output. Then you create a slice of those structs, a table, and you just loop over them in your test function.
It makes it so incredibly easy to add new test cases. You just add one more line to that table. You don't have to write a whole new function. It encourages you to be thorough and test all the edge cases because it's so low friction.
And then the most emphatic point in the entire research stack, the single most important tool, the race detector.
Arguably Go's most important tool for production systems. You run your tests with the DES race flag, Go test race.
And what does that do?
Concurrency bugs data races are basically impossible to find manually. They happen 1 in a million times, usually at 3 a.m. on a Saturday. The race detector instruments your code at compile time to watch for any unsynchronized reads and writes to shared memory.
So it finds the bugs for you.
It finds them. And the expert rule is, if the race detector says there is a race, there is a race. Do not argue with it. Do not say, oh, that's unlikely to happen. Fix it. Always run your CI/CD pipeline with the race detector enabled. It has a performance cost, so you don't run it in production, but for your test suite, it is non-negotiable.
Okay, listener, take a deep breath. We are now entering the advanced engineering section. The notes call this the dark arts.
This is where we stop looking at code as just text, and we start looking at it as physical RAM layout.
Let's start with struct padding and alignment. This blew my mind. The order of the fields in my struct actually matters.
It matters for your memory usage.
Yeah.
A lot. Modern computers read memory in words, usually 8 bytes on a 64-bit system. They are much faster if the data is aligned to these 8-byte boundaries. So if you have a struct with a bool, 1 byte, followed by a float 64, 8 bytes, the compiler can't just smash them together. It has to add 7 bytes of padding, of empty space, after the bool so that the float starts on a clean 8-byte boundary.
So you're just wasting 7 bytes of empty space in every single one of those structs.
Which is fine for one struct. But what if you have 10 million of these in a cache?
Yeah.
The nodes say you could be wasting 80 megabytes of RAM just on empty air.
And the fix is just reordering the fields in the struct definition.
That's it. You group the fields by size.
Mm-hmm.
Put all the 8-byte fields first, then the 4-byte fields, and then the smaller ones. There's a tool called field alignment in the Go tool chain that will analyze your structs and tell you the optimal ordering. It is literally free optimization.
That is wild. Next up, the garbage collector knobs. Go's GC is known for being low latency, but there's something called the Kubernetes trap.
This is a classic DevOps nightmare. By default, Go's runtime looks at the memory of the host machine to decide how aggressively it should run the garbage collector.
The physical server.
Right, so if you run your Go application in a Docker container that's restricted to 1 gigabyte of RAM, but the server it's on has 64 gigs, Go thinks it has 64 gigs of headroom. It gets lazy. It decides, hey, I don't need to garbage collect yet. I have plenty of room.
And then the container hits that 1 gigabyte segroup limit and boom! OM kill.
Exactly. The Linux kernel just kills your process without warning. The fix used to be complex, but now we have the GoMem limit environment variable. You set it to, say, 900 millibeat. Go's runtime then knows, okay, I have a hard ceiling, and it will run the GC much more aggressively to stay under that limit. It solves the problem instantly.
We mentioned the slice memory leak earlier, that tiny slice holding onto the massive array. The notes mention strings clone as the fix. Can you elaborate?
Sure. If you have a slice of bytes, you can use bytes.clone. If it's a string, strings.clone. What these functions do is create a fresh copy of just the data you need in a new, perfectly sized memory allocation. The original massive array then has 0 references pointing to it and can be immediately garbage collected. It breaks the link to the piano.
Got it. Let's talk about advanced I/O, streaming versus reading it all into memory.
A junior Go engineer reads a file with OS read file. They slurp the whole thing up into a byte slice. A senior Go engineer streams.
I/O reader and I/O writer.
These interfaces are the heart of Go's I/O system. They let you build pipelines of data. You can take an incoming HTTP request body, which is an I/O reader, pipe it through a gzip decompressor, pipe that into a JSON decoder, and pipe that into a file on disk, which is an I/O writer.
And the memory usage is tiny.
Tiny. You could be processing a gigabyte-sized file, but your application's memory usage might only be a few kilobytes because you're only ever holding one small chunk of the data at a time. It is the difference between a toy app and a truly scalable system.
Speaking of scale, JSON. Encoding JSON is great, but it has a performance cost.
It does. The standard library uses reflection at runtime to figure out the tags on your struct and how to map the JSON fields. For most applications, that's totally fine.
But not for high-frequency trading.
Not if you're handling massive API throughput. That reflection overhead adds up. For those cases, the community uses code-generated marshallers like EasyJSON or FJSON. You run a tool over your code, and it writes the explicit Go code to parse the JSON at compile time. It's way, way faster, but it does add a build step.
Network hygiene. This one is a big red warning label. HTTP.default client.
Never, ever, ever use it in production.
Why? I mean, it's the default. It's so convenient.
Because it has no timeout. None. 0. If you use the simple HTTP.get function, you are using the default client. If the server you are calling hangs and never sends a response, your Go routine will wait. Forever.
And if you have a lot of requests coming into your server and each one makes one of these outgoing requests,
You leak Go routines, they just pile up, waiting forever, consuming memory until your server falls over and crashes. You must always create your own HTTP.client and explicitly set a timeout value. It's a 5-line fix that will save your production environment.
okay, the dark art section ends with a big warning. CGO and the unsafe package.
CGO is the mechanism that allows Go to call C code. The advice from seasoned Go developers is, avoid it like the plague.
But why? Isn't C fast?
C is fast, but the call from Go into C is not. It has significant overhead. It ruins the Go scheduler because it has to lock the OS thread for the duration of the C call. It makes your builds incredibly complicated because now you need C libraries and a C compiler on the build machine.
Huh?
You lose the beautiful, simple, static, binary portability that is one of Go's best features.
So only if you absolutely have to.
Only if you absolutely need a library like FFmpeg, that is impossible to rewrite in pure Go.
And unsafe. The name itself is a warning.
It does exactly what it says. It lets you bypass Go's type system and memory safety.
Hmm?
It lets you treat an integer as a pointer. If you make a mistake, you don't get a nice panic. You get silent memory corruption or a major security vulnerability. Just don't touch it unless you are writing the core of a database or high-performance serialization library.
Let's move to segment 6, production ecosystem and architecture. We have built the app, now we need to actually run it. Let's start with logging.
Log. Println is useless for production.
Ouch. Harsh but fair.
It prints a simple text string, user logged in. That's fine if you're a human reading a terminal, but in production, you have millions of log lines from hundreds of services. You need to be able to search and filter them. You need structured logging.
So logging in a format like JSON.
Exactly. Use the standard library slog package or a popular third-party one like Zap. You log key-value pairs. Level info, MSG, user logged in, user root 123. Then you can go to your logging system and ask, show me all error logs for user root 123 from the payment service in the last hour. You cannot do that with plain text strings.
And this ties into distributed tracing.
OpenTelemetry is the standard now. In a microservices world, a single user request might hit 5 different services before it's done. If it fails, where did it fail? Tracing attaches a unique ID to that request that travels with it across all service boundaries. You can then visualize the entire waterfall and see exactly which service was slow or returned an error.
Databases. We all use SQL. What's the Go way to interact with the database?
First and foremost, security. Never, ever concatenate strings to build a SQL query. That is SQL injection 101. You must use prepared statements with placeholder values like a question mark.
And what about ORMs? People coming from other languages love their ORMs.
Go has GoRM, which is quite popular. But for that engineering reality we're talking about, the community trend is strongly towards a tool called SQL C.
SQL C. How does that work?
It's brilliant. You write your raw, normal SQL in .SQL files, select EAD, named from users where EAD. Then you run the SQL C tool, and it reads your SQL queries and generates type-safe Go code to execute them.
So you get the full control and performance of raw SQL, but the compiler-checked safety of Go types.
Exactly. There's no runtime reflection overhead like with a heavy ORM. It is truly the best of both worlds.
Microservices. When do you choose REST versus gRPC?
For the outside world, your front-end application, your public APIs, use REST. It's JSON over HTTP. It's universal. Every developer understands it. But for internal service-to-service communication between your own microservices, use gRPC.
Because it uses protobufs, which are binary.
Right. They are smaller on the wire, faster to serialize and deserialize, and they give you strongly typed contracts. You define your API in a .proto file, and it generates all the client and server code for you. You eliminate a whole class of bugs related to mismatched API expectations.
Dependency injection. In Java, you have Spring doing its magic. In Node, you might use something like Nest.js. In Go,
You have main.go.
the manual approach.
Go developers, by culture, prefer explicit wiring. In your main function, you create your database connection. You pass it to your repository struct, you pass that repository to your service, and you pass that service to your HTTP handler. You can see the entire dependency graph right there in the code.
But for huge, huge monoliths, that could get complicated.
It can. For those cases, there's a tool from Google called Wire. It does compile-time dependency injection. It analyzes your code and generates the manual wiring code that you would have written yourself. The key is to avoid runtime reflection-based DI containers. They hide dependencies and tend to crash at runtime when you're missing something.
Okay, segment 7, security and the uncomfortable truths.
On the security front, things are getting much better. There's an official tool now called Golang. It scans your code for known vulnerabilities, but it's incredibly smart. It analyzes the call graph.
What does that mean, the call graph?
It means if you import a library that has a known vulnerability, but your code never actually calls the specific vulnerable function within that library, Golang won't flag it. It reduces the noise from false positives massively compared to other scanners that just look at your go.mod file.
And fuzzing is now built in.
Native since Go 1.8. It's a fantastic feature. Instead of writing tests with specific hard-coded inputs, you write a fuzz test and let the fuzzer throw millions of rounds of random malformed garbage at your functions to see if it can make them crash. It finds edge cases that a human would never think to test.
Now, let's get to the uncomfortable truths. The things that make you want to tear your hair out sometimes when you're writing Go.
The nil interface. This is the classic. An interface variable holding a nil pointer is not itself nil.
Okay, explain that slowly. This sounds like a logic puzzle.
An interface in Go is actually a tuple under the hood. It stores a type value pair. So if I have a pointer to a struct, let's say my struct, and that pointer's value is nil, and then I assign it to an interface variable, that interface variable becomes type mystruct value.nil.
So the interface itself is not nil because the type part is filled in.
Exactly. So your check if my interface dual nil will return true even though the value inside it is nil, and then you try to call a method on it and your program panics. It catches every single Go developer at least once.
What's the fix?
The fix is to be disciplined. From functions that return an interface, always return an explicit untyped nil, not a nil pointer of a concrete type.
And enums, or the lack thereof.
Go doesn't have them. We use const blocks and a thing called iota to create incrementing integer constants, but there's no real type safety. If I have a function that expects a status, which is just an int, I can pass the number 100 to it, even if 100 isn't a valid status. You have to add manual validation.
And finally, JSON tags relying on strings.
A simple typo. You're trying to tag a field JSON.userid, and you accidentally type JSON.userid. The field just vanishes from your JSON output, silently. No compiler error, no runtime error, it's just gone.
It sounds like Go demands a lot of discipline from the developer.
It absolutely does.
Yeah.
Gives you simple, powerful tools, but it trusts you and demands that you use them correctly.
So we've reached the end of our deep dive. What is the takeaway here? What is the senior engineer mindset when it comes to Go?
The mindset is to stop fighting the simplicity. Stop trying to make Go look like Ruby or Java with clever abstractions. You have to accept the verbosity.
That if error nil is a feature, not a bug.
Exactly. It's visibility, it's clarity. And you have to accept copying code. There's a famous Go proverb, a little copying is better than a little dependency. Don't make a shared library or a complex abstraction until you've copied the code 3 times and you truly understand the pattern.
Think in data.
Yes. Visualize the memory layout of your structs. Map out the concurrency with coroutines and channels. Understand that you are managing physical resources, not just abstract ideas.
And finally, value stability.
Go has an incredible backward compatibility promise. Your code from 2015, written for Go 1.5, will very likely compile and run perfectly fine today. In a world of constant breaking changes and framework churn, that stability is an incredibly valuable feature for businesses.
It brings me back to that final thought in our outline. Go is, well, it's boring.
It is. It's the Borat nature of Go. It's not flashy. It's not academic. It doesn't have the latest features, but it runs the infrastructure of the internet. It runs the cloud. It's what Docker and Kubernetes are built on.
So the provocative thought for our listeners is this. Is boring actually the ultimate feature for modern software engineering?
When you are the one getting woken up by a PagerDuty alert at 3 a.m. because a server has crashed,
Yes.
boring is exactly what you want.
Right.
You want predictable, readable, stable, boring code that just works.
I think that's the perfect place to leave it. If you want to build the next layer of the internet, maybe it's time to get a little boring. Thanks for listening to The Deep Dive.
Keep learning.